Dear students, in today's lecture, we will discuss skewness and kurtosis for any curve. First of all, we talk over Karl Pearson beta and gamma coefficients. These beta and gamma coefficients given by Karl Pearson are based over, say, central moments, like formula for beta 1. mu3 whole square upon mu2 whole cube. mu2 and mu3 are second and third moments about mean, or second and third central moments, which we have discussed in previous lecture. And then beta 2 is mu4 upon mu2 square, means depends upon mu2 and mu4, that is second and fourth central moments. So using second, third and fourth central moments, we can calculate Karl Pearson's beta coefficients, and using beta coefficient, that is beta 1 and beta 2, gamma coefficients of Karl Pearson can easily be obtained, like gamma 1 is positive square root of beta 1 and gamma 2 is beta 2 minus 3. So that is more or less about beta coefficient, because gamma coefficients depends upon beta coefficients and beta coefficients depends upon second, third and fourth central moments. Let's talk about utility of this beta gamma coefficient. We use these coefficients to measure skewness and kurtosis, which we will discuss one by one in this lecture. We start with skewness. The term skewness is used to describe the symmetricity of a curve. That is, for any particular curve, if we want to know about the symmetricity of a curve with respect to a particular straight line, maybe vertical, maybe horizontal, then we have to use to calculate skewness. And the formula for coefficient of skewness is discussed here. There are many different results given for measuring skewness for any curve, but especially this formula is popular and it depends upon beta coefficients of Karl Pearson. That coefficient beta 1 and beta 2 can be observed there in right hand side of that formula. The coefficient of skewness is here defined as Sk, and it's equals to root beta 1 into beta 2 plus 3 upon twice of 5 beta 2 minus 6 beta 1 minus 9. Means beta 1 and beta 2 are independent variables for this expression, and Sk depends upon beta 1 and beta 2. As it can easily be seen, if beta 1 equals to 0, Sk also reduces to 0. So here we have to discuss three different things: when Sk becomes positive, when Sk becomes negative, and when it becomes 0. It becomes 0, it can easily be said for beta 1 equals to 0. Then for particular values of beta 1 and beta 2, it may be positive or negative. As per these three choices of Sk, 0, positive or negative, the skewness of the curve can be described, which we will see through diagrams in next slide. As I was discussing in final term of previous slide, that for three different choices of Sk, 0, negative or positive, the symmetricity of curve looks different. When Sk is 0, that is beta 1 is 0, we have seen it discussed in previous slide, then curve is in symmetrical view, and in that case that vertical line is showing mean, median and mode. All three are equal, and we know that all three are equal for a normal curve, the curve of normal distribution, which we have discussed before. So it is the case of normal distribution for which Sk is actually 0 or skewness is 0. So whenever 0 skewness is there, means curve is not skewed, then it is symmetrical, and with respect to that line where mean, median and mode all three are equal, the curve is symmetric both the sides. And whenever we have Sk less than 0, negative value of Sk, then curve is known as negatively skewed curve, and in that case, as it's written there, long tail on left of mode, that is that particular straight line is straight line showing mode of that particular curve for which Sk is less than 0, and a long tail on left side of mode can be seen for negatively skewed curve, and median and mean are also seen over left hand side of that mode for such curves. And when we have Sk as positive value, then it is another kind of skewness, positive skewness, or the curve is known as positively skewed curve, and that is line of mode for such curves. And long tail on right of mode can be seen, that means median and mean can be seen over right hand side of that mode, and long tail is easily observed in comparison of left hand side. It's there in right hand side for positively skewed curve. So that is about different kind of symmetricity. It's symmetricity with zero skewness. Then we have two cases where skewness can be seen, negative kind of skewness and positive kind of skewness. Let's define kurtosis. This term kurtosis is used to describe the peakedness of a curve. That means a curve is peaked or not, or what kind of peak is given there for curve, and it all depends upon beta 2, mu 4 upon mu 2 square, or gamma 2, which is nothing but a term dependent of beta 2 minus 3. So when we have value of beta 2 with us, we can talk over that kurtosis part of a curve. If beta 2 is 3, then that distribution is said to be normal, and the curve is a normal curve. Normal kind of peak can be seen, and that curve is known as mesokurtic. Here is can be seen in that diagram. When beta 2 is 3, a normal peak is there for the curve, which is known as mesokurtic. And if beta 2 is positive, greater than 3, the distribution is said to be more peaked in comparison of normal peaked curve, and the curve is known as lapokurtic, as it can be seen there, beta 2 greater than 3. So lapokurtic curve is observed there, and when beta 2 less than 3, the distribution is said to be flat topped. That means peak is almost flat there, and then curve is known as bradycardic, as it can be seen there, bradycardic curve, where that peak is almost flat when beta 2 less than 3. So here in this lecture we discussed skewness and kurtosis, which depends upon Karl Pearson's beta and gamma coefficients.